Okay, now that we've practiced the exercise in Statistics Without Tears, I'd like to, in this video, do a real-life example, or at least it's a real-life example in my fantasy world where I'm the queen over my own state. So before you go on from this, you should get yourself a calculator and a piece of paper and a pen or pencil, because you're going to be actually doing some calculations, pausing the video and doing some calculations. Okay, so the state of Fagmania has a statute that prohibits factories from emitting more than 60 tons of pollutants per month. This is assuming a 30-day month, and then that gets prorated for shorter and longer months. So Fagmania has a hardworking EPA, Environmental Protection Agency, but just like the United States EPA, it has a very lean staff, can't be in 12 places at once. So it's going to be too expensive to have my inspectors sample all of the factories in Fagmania every day of every month. So my best alternative here is to take random samples. So here on the slide, you see a picture of the Spew and Profit Chemical Company factory, or SAP factory for short, SAP factory. And my FEPA scientists decide to use sampling to check up on this factory. They know that under the statute, they have to show that they can be 95% confident that SAP factory is emitting more than 60 tons of pollutants per month in order to find the factory in violation of the statute. So they go out and sample the pollutants from the factories on 6 random days out of a 30-day month. Okay, now stay with me here. On this slide, I'm actually showing you the actual amounts of pollution emitted every day in November, which is a 30-day month. So this is shown in these columns here. These are the peek behind the curtain amounts that were actually emitted every day in November. So that's our true population amount of emissions. But our scientists, of course, don't know all that. They only have the data from these 6 random days that they sampled. So the 6 numbers here add up to 11.4 tons. Okay, 11.4 tons is the sum of the pollutants there, and dividing that by 6, we get a sample mean here of 1.9. Okay, now cheating here and peaking, if we add up all the pollutants from the entire month, right, we get 63 tons. Dividing that by 30, the actual population mean is 2.1 tons. So considering that we only have a sample of 6, getting a sample mean of 1.9 is not a very bad estimate to what the real population mean is. By the way, also, we're sort of suspending the notion here in this example of a minimum sample size being 30, just for the sake of doing this example. So we're pretending that a sample of 6 is adequate. Okay, so now I'm showing you here the actual math for calculating the variance of our sample. The variance of our sample. And then, of course, we take the square root of that. Here's the variance, 0.403, but we know we have to take the square root of that to get the standard deviation. I've also done that math for you. So our variance here was 0.403, and the standard deviation is 0.63 tons, 0.63 tons. Okay, so remember our goal here is to estimate the monthly tonnage of SAP factory, right? And the sample mean is going to give us the best estimate of the true population mean. We're trusting that our sample of 6 is enough. And we know our sample daily mean for pollution, again, was 1.9 tons. So our best guess at this point is that the mean per month tonnage is 57 tons, right? Multiplying 1.9 times 30. So that actually would be within the allowable limits. But we want to do some statistical calculations that will actually get us a range of possible monthly outputs at that 95% confidence level that is required by our statute. So we have to construct a confidence interval around that 57-ton estimate. So remember, there's 2 basic aspects to a confidence interval, right? Number 1 is the range within which the true value is thought to fall. And then, of course, number 2, our confidence or degree of certainty that the true value actually does fall within our calculated range. All right, so remember, to determine how much a particular sample mean is likely to vary from the actual population mean, we use this calculation, right? The standard error of the sample mean. Here's that formula once again for you. We take the standard deviation of our sample, which is here, 0.63, and we divide that by the square root of the size of our sample. The size of our sample is 6 here. Okay, and doing that math, we find that the standard error of the mean here is 0.26 tons. Okay, the next thing is we know that we can count on our normal distribution to derive the probability that a given observation is going to be a certain number of standard deviations away from the mean value, right? So let's start here with our 68% confidence interval, even though our statute requires 95. Let's just figure out what our 68% confidence interval would be. So starting with that, how many standard deviations are going to be encompassed in that interval? 1, right? 1 standard deviation above and 1 standard deviation below. So now pause the video and go ahead and figure out the 68% confidence interval. Okay, so hopefully you got this correct. If we plot out 1 standard error above and below our sample mean daily pollution output here of 1.9 tons per day, we see that we can be 68% confident that our actual tonnage per day falls between 1.64 and 2.16 tons. Or multiplying those values times 30 days, we can say we're 68% confident that the monthly pollution output is between 49 and 65 tons per month. So here's a question for you. Based on the 68% confidence interval, can we conclude that the Fagmanian statute is being violated here? Remember, anything greater than 60 tons per month is illegal. Can we say that the statute's been violated based on these data? No, we can't, right? Because this lower boundary here falls below the prohibited tonnage of 60. All right, but we know our statute requires a determination to the 95% confidence level. So how many standard deviations above and below the sample mean will that encompass? Hopefully you got the answer right off the top of your head, but it's going to be 2 standard deviations above and below. So now pause the video and go ahead and figure out the 95% confidence interval. Okay, hopefully you came up with this answer. We can be 95% confident that our actual tonnage per day falls between 1.38 and 2.42 tons per day, or multiplying those values times 30, we can be 95% confident that the true monthly value falls between 41 tons per month and 73 tons per month. So here, obviously, we have a wider range than our 68% interval. So now, given our statutory requirement under our Fagmanian statute that requires the 95% confidence interval, can we conclude that the Fagmanian statute is being violated here? Once again, the answer is no. And yes, I know there's a mistake on this slide. These are mistakes, these values here. But you probably already would have figured out that we knew we weren't going to meet this requirement when we saw we didn't even get there with our 68% confidence interval, right? Because this lower value falls below the statutory requirement. Now though, suppose our sample mean ended up being 2.8 with a standard error of the mean of 0.3. That would translate here into a 95% confidence interval of 66 tons per month to 102 tons per month, right? Now, can we meet the requirements of the statute to show that SAP factory is in violation? Yes. Yes, we would be able to do that. Okay, so that's the end of that example. But I do have one more thing I want to talk about on this video. So we've been working with standard error of the mean, which allows us to take numerical data and come up with confidence intervals, but sometimes we don't have data points that have numerical values like exam scores or tons of pollutants, right? Sometimes we have category type variables, like for example in our Gallup polls where sample subjects just answer a multiple choice type question. So the question is, how can we come up with confidence intervals for that kind of data? We can't calculate the standard error of the mean because this kind of data isn't going to give us a mean and a standard deviation. So you saw in Statistics Without Tears that what we use instead is called the standard error of the proportion. So I have an example here using the same numbers that are used in the Statistics Without Tears section on standard error of the proportion, but I'm just using a different data story. So you can tell this is an example from a few years back. Suppose you're trying to determine the percentage of Obama supporters in a neighborhood in San Francisco. So let's say you take a representative sample of 100 residents of the neighborhood. 80% of them are supporters, 20% are not. And I'm sorry, this isn't just Obama supporters, it's Obamacare supporters. All right, So that's all very interesting. 80% said they were supporters, 20% they weren't. But as a pollster, you don't want to just make a statement about those 100 people that you sampled, right? Because as a pollster, you want to make a statement about the percentage of supporters in the entire population of that neighborhood, which you think is about 200,000 people or so. You're not positive, and in this example, it doesn't matter because we're assuming you took a random sample. All right, so in fact, what you want to do here is you want to get way up into that 95% confidence interval to be able to make a statement that you're 95% confident that the percentage of Obamacare supporters in the neighborhood is within a certain range. And that we do by calculating the standard error of the proportion. So this is from Statistics Without Tears, starting on page 99. Here is the formula for computing the standard error of the proportion. It is the square root of this entire number under the square root system, symbol. So square root of the proportion of supporters multiplied by the proportion of non-supporters divided by the number of people in the sample. So again, first you do the multiplication, then you do the division, and then you take the square root of that entire result of those calculations, all right? And so the formula here uses P and Q for the two proportional values. Statistics Without Tears uses P1 and P2, but the result is obviously the same. Okay, so we want to take the results we got, plug them into this formula, right? But then what? We want to take this standard error of the proportion value that we come up with and translate that into a confidence interval like this, right? So we want to be able to say that on the basis of our data, we can say with 95% confidence that between blank and blank of the population are Obamacare supporters. And that, in fact, is just what this formula allows us to do, because once again, we can rely on our 68, 95, 99, 99.7 confidence intervals from our normal curve once we calculate our standard error of the proportion. All right, so let's do the math. We multiply P times Q. In this case, we have 0.8 times 0.2, right? Because 0.8 is 80%, 0.2 is 20%, right? We multiply that, that is 0.16. Then we know we have to divide that here by our sample size of 100, okay? And we come up with 0.0016, and we have to take the square root of that, which is a nice, neat 0.04, which translates, of course, into 4% in our example. All right, so from there, it's pretty easy to come up with our 95% confidence interval. We can say with 95% confidence that between 72 and 88% of the population are supporters, right? You start with 80% supporters, and then you go down 2 standard errors of the proportion to 72, and you go up 2, and you get 88% are supporters. Okay, and one other important thing to know and remember about proportions and category variables is that as a general matter, it's going to be tougher to get narrower, more precise confidence intervals than it's going to be with numerical value samples. We can see when we're dealing with proportions and category variables instead of numerical data, we're really going to need to increase our sample size a lot to get a narrower confidence interval range. And in fact, Statistics Without Tears points this out on page 100. due to the fact that the standard error of the proportion only gets influenced by the square root of the sample size, we need to, for example, increase our sample size by a factor of 4 if we want to cut down our confidence interval by half, right? So in our political example, if we increased our random sample size by a factor of 4 to 400 people instead of 100 people, which of course would involve a lot more work and time and resources, then our standard error, the proportion, if you do the math, it would be reduced, but it would only be reduced by half to 2%. So increasing our sample size by a factor of 4 only gives us a reduction of 1/2. So then our confidence interval, our 95% confidence interval, would be that between 76 and 84% of the population are Obamacare supporters. That's assuming that we got that same 80-20% split. Okay, this is the end of video lecture 13.